Good morning, everyone. Thank you for being here today. I'm pleased to welcome you to this presentation on sterility testing using the membrane filtration method. My name is Dr. S.K. Singh, and I hold a PhD in this field. Over the next few minutes, we'll explore the key aspects of this important technique, including its principles, procedures, and significance in quality control. So let's get started and delve into the fascinating world of sterility testing. Let's begin with the concept of sterility testing. This is a crucial process that ensures products are free from viable microorganisms, which is essential for patient safety. It's especially critical for products like parenterals, ophthalmics, and biologics, where the risk of infection must be minimized. One of the key methods used in sterility testing is membrane filtration. This technique is preferred, particularly for clear and filterable products, because it allows us to effectively trap any microorganisms on a membrane for easy detection. It's also important to note that membrane filtration is recommended by major pharmacopoeias, such as the United States Pharmacopoeia and the European Pharmacopoeia. These guidelines help standardize testing procedures across the industry, ensuring consistency and reliability in our results. Overall, understanding and implementing proper sterility testing methods, like membrane filtration, is vital for maintaining product safety and meeting regulatory standards. Let's take a closer look at the regulatory basis for sterility testing. First, we have the USP 71 sterility tests, which set the standards we need to follow. Then, there's the PH, your 261 sterility, another important guideline. Additionally, the World Health Organization provides their own recommendations to ensure safety and quality. All of these sources emphasize some key requirements. First, we must maintain aseptic conditions throughout the testing process to prevent any contamination. Second, we need a validated method, meaning the procedure has been thoroughly tested and proven to work reliably. And third, environmental monitoring is essential to verify that the testing environment remains free of microbial contamination. Now, let's discuss the core principle behind the test. A sample is passed through a sterile membrane filter, typically 0.45 micrometers in pore size. Microorganisms, if present, are retained on the surface of this filter. Next, the filter is incubated in a nutrient-rich growth media. If microbes are present, they will grow during incubation, causing turbidity or cloudiness in the medium. This change indicates microbial growth, confirming whether the sample is sterile or not. So, these guidelines and principles help us ensure that our products meet strict safety standards, safeguarding patient health and maintaining quality across the board. Now, let's walk through the procedure overview for this process. First, you'll need to assemble a sterile filtration unit. This step is crucial to prevent contamination and ensure accurate results. Once everything is set up, pass your sample through the membrane, which acts as a filter to trap any microorganisms present. After filtration, it's important to rinse the filter carefully to remove any potential inhibitors that might interfere with growth detection. Then, transfer the membrane to the appropriate culture media, which provides the nutrients necessary for any microorganisms to grow. The next step is incubation, where you'll keep the sample under controlled conditions to allow growth to occur. Finally, observe the culture for signs of growth, which indicates the presence of microorganisms. Moving on to the apparatus and materials you'll need, start with a membrane filter that has a 0.45 micrometer pore size, ideal for trapping bacteria and other microbes. You'll also need a filtration assembly, which can be made of glass or plastic, and a vacuum pump to create the necessary suction for filtration. Sterile forceps are essential for handling the membrane safely without introducing contamination. Regarding the culture media, you'll be using fluid thioglycolate medium, or FTM, which is excellent for supporting anaerobic bacteria, and soybean casein digest medium, or SCDM, which is versatile for a broad range of microorganisms. These media help ensure that any microbes trapped on the filter will grow and be detectable, providing reliable results for your testing process. Let's start by understanding how we interpret the results of this test. If there's no turbidity in the sample, it means the sample is sterile, so we consider it a pass. On the other hand, if we observe turbidity, that indicates contamination, and the result is a fail. Now, to confirm whether contamination actually exists, we perform additional tests. These include subculturing the sample and conducting microscopic examinations. The detailed procedure begins with filtering the sample under aseptic conditions to prevent any external contamination. After filtering, we rinse the filter with a sterile fluid, such as peptone water, to wash away any residual particles. Next, we divide the filter into two parts. One part is incubated at 30 to 35 degrees Celsius in a fluid thioglycolate medium, or FTM, which is ideal for growing many types of bacteria. The other part goes into soybean casein digest medium, or SCDM, at a slightly lower temperature of 20 to 25 degrees Celsius to support the growth of different microorganisms. Finally, we incubate both cultures for up to 14 days. This extended incubation period helps ensure that slow-growing organisms are detected, giving us a thorough assessment of contamination. By following these steps, we can confidently determine whether the sample is contaminated and ensure the safety and sterility of our products. Now, let's talk about the advantages of the membrane filtration method in sterility testing. This technique is especially suitable when dealing with large volume samples, which is a big plus because it allows us to test more material efficiently. It also effectively removes antimicrobial substances that might otherwise interfere with the detection process. Another key benefit is its high sensitivity, meaning it's very good at detecting even small numbers of microorganisms. Plus, in some cases, it provides faster detection compared to direct inoculation methods, helping us get results more quickly. However, like any method, it has its limitations. It's not suitable for oily or viscous products, as these can clog the filters or prevent proper filtration. Similarly, samples that are non-filterable can't be tested with this method. We also need to be aware of potential risks, such as filter blockage, which can disrupt the process, and false positives that might occur due to environmental contamination. So maintaining a sterile environment is crucial. Overall, membrane filtration is a powerful tool in sterility testing, especially when dealing with large volumes, but it requires careful consideration of the sample type and potential pitfalls. Now, let's take a look at some of the key applications for the sterilization processes we've been discussing. First, we have injectable drugs, such as saline and antibiotics. These are critical medications that must be sterile to ensure patient safety. Then, we have vaccines, which require a high level of sterility to prevent any risk of infection. Water for injection, or WFI, is another essential application, serving as the sterile water used in various pharmaceutical preparations. Lastly, ophthalmic solutions, like eye drops, also need to be sterile to avoid contamination and protect vision. These examples highlight how vital sterilization is across different medical and pharmaceutical products, ensuring safety, efficacy, and trust in healthcare. Let's talk about method validation, which is a crucial part of our process and is required by regulatory guidelines. When we validate our methods, we need to focus on several key parameters. First is sterility assurance, ensuring that our products are free from any microbial contamination. Next is the growth promotion test, which confirms that our culture media can support microbial growth as intended. We also perform a method suitability test, which helps us verify that our testing methods are appropriate and effective for the specific application. Overall, these parameters demonstrate the reliability of our methods, giving us confidence that our testing is accurate and consistent. Validating our methods according to these guidelines ensures that our entire quality assurance process remains robust and compliant, ultimately supporting the safety and efficacy of our products. Now, let's talk about some key precautions to ensure safety and effectiveness in our procedures. First, maintaining an aseptic environment is crucial, and that's where the laminar air flow comes into play. It creates a sterile zone, reducing the risk of contamination. Next, always use sterile instruments. This might seem straightforward, but it's fundamental to prevent introducing any unwanted microbes into the process. Another important point is to avoid contamination during transfer. Whether you're moving materials or samples, be mindful of how you handle them to keep everything as clean as possible. And finally, performing environmental monitoring is essential. Regular checks help us ensure that our environment remains sterile and that our precautions are working effectively. All these steps tie back to our overall goal: maintaining a safe, sterile environment to achieve optimal results and prevent any potential complications. Let's wrap up with the conclusion. Membrane filtration has truly become the gold standard for sterility testing. It's widely accepted by global pharmacopoeias, which highlights how universally trusted and standardized this method is. This technique not only helps ensure the safety of our products, but also keeps us in compliance with regulatory requirements. When it comes to filterable pharmaceutical products, membrane filtration is the preferred method, mainly because of its efficiency and reliability. So, in the overall context of sterility assurance, membrane filtration stands out as the most effective and trusted approach. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional information you might need. Thank you so much for your time and attention today. We truly appreciate your interest and engagement. If there's anything more you'd like to discuss or clarify, please feel free to contact us. Once again, thank you, and we look forward to connecting with you further.